Can I be honest? When I first heard about data warehouses, lakes, and lakehouses, I didn't understand the differences between them. They sounded like marketing buzzwords rather than real technological differences. I laughed at the jokes about data cabins or data ranches being the next big thing, but as I began researching them and learning about where they came from and how they evolved, the differences became more clear and the reason for the names were more obvious. There are, in fact, real differences between the technologies, and once we understand the context they developed in, the names actually make sense. Let's start with data warehouses. Despite the name change, a data warehouse is just a specialized database. They evolved because traditional databases were built for online transaction processing, or OLTP, leading to design decisions that were incompatible with analytics. Data warehouses, on the other hand, were designed for online analytical processing, or OLAP, and optimized for large datasets. They followed the same structural approach with rows, columns, and tables with well-defined schemas that were designed upfront for consistency and predictability. The schemas could change, but it required migrating existing data to match the new structure. This structured approach was ideal for analytics, allowing for SQL queries that produced predictable results. And performance was good because data followed patterns that were easy to optimize. The basic philosophy of a data warehouse is called schema-on-write. We define the table structure up front with precise data types and constraints. For example, here we create the customer table and define all fields and types first. Then we write data that precisely matches the defined schema. This works well for clearly defined data structures, but the data landscape has evolved. As the internet grew, people began using it in more of their daily life. Meanwhile, businesses tried to capture more attention from them and recorded every interaction in extensive log files. Mobile devices created streams of user activity. Internet of Things sensors produced time series measurements. And social media brought unstructured text, images, and videos. Today, machine learning is demanding even more to create diverse training datasets. We are capturing more data than anyone anticipated, and it doesn't fit into rows and columns anymore. This explosion posed a problem for warehouses. These stable, well-defined schemas became rigid when changes were needed, requiring complex migrations, taking hours or days. In practice, this led to a reluctance to evolve the schemas. Meanwhile, much of today's data, including images, videos, and documents, doesn't fit into relational structures. And while modern data warehouses have improved handling of structured types like JSON, they still don't have effective solutions for less structured types. How do we store a video file in a database table? What about an XML document? And with terabytes of data, traditional warehouse architectures struggled to scale economically. The world moved beyond structured data, but storage solutions hadn't kept up. This is where the Hadoop Distributed File System, or HDFS, enters the picture. It allowed systems to store media files and documents without needing them to fit into a traditional table structure. However, it didn't come with SQL capabilities out of the box. Those had to be added using tools like Hive. This created a foundation for storing data first and adding structure later. Object storage like Amazon S3 and Google Cloud Storage evolved from this basic foundation. It offers storage for just a couple of cents per gigabyte, compared to traditional storage at 10 to 15 times the price. It handles any file type, including CSV, JSON, videos, images, and documents. And it does it with near infinite scalability. Meanwhile, multiple teams can access the data simultaneously without performance degradation. But storing data is only half the battle. We also need to analyze it. Even if object storage can support countless formats, we still need to make sense of it. This is the origin of data lakes. Think about a real lake, like the water kind, not the data kind. Lakes have many sources, like streams, rivers, and rainwater. The lake doesn't care where the water comes from and treats it all the same. Everything becomes one homogeneous mixture. But to use the water, you have to separate and filter it first. Object storage works the same way. It doesn't differentiate between file types or impose structure on them. But if you want to analyze the files, you will need to apply structure to them first. This new paradigm flipped our philosophy to schema-on-read. Instead of enforcing structure when writing, we write raw data. Here, we're copying JSON files into object storage without processing. Then we figure out the structure when analyzing, such as converting the JSON files into tables. Finally, we query the extracted structure. The revolution was that suddenly all of those raw files became queryable. Meanwhile, it shortened the development cycle because teams could ingest data immediately without spending long cycles of upfront schema design. Essentially, the complex modeling decisions could be deferred until later in the pipeline when the requirements were better understood. It's important to understand that unstructured data isn't completely unstructured. Video files have an internal structure of frames divided into pixels, but we don't impose structure when the data is written, and it varies from file to file. A JPEG image has a very different structure from a PNG. Think of unstructured data as data where the structure isn't known ahead of time. This makes it difficult to fit into traditional databases. But it fits perfectly into data lakes where we don't force it to conform to an existing structure. This makes data lakes powerful. We could store files in any format, including JSON, CSV, or Parquet. Files could be stored side by side, keeping related documents and media together. And we can interpret the files multiple ways, changing schemas based on our needs. Essentially, each team extracts the fields that matter for their use case, ignoring anything extra. Data scientists could query and build reports without modifying sources or needing engineering help. Unfortunately, this success created new problems. As data lakes grew, they became unmanageable. Anyone could store anything anywhere, polluting the object store with disorganized files. Meanwhile, the teams didn't just apply different schemas to the data, they also applied different interpretations, producing conflicting results. And real-time data arriving as individual events created thousands of tiny files scattered across the lake. Query engines spent more time opening files than processing data. Finding consistent data became like looking for a needle in a haystack. Our beautiful lake had become a swamp. In a traditional database, when we have performance issues, we can work around them by restructuring or adding database indexes. But these optimizations require a predetermined structure. With no enforced structure, query engines struggle to optimize, leaving no escape hatch for performance issues. The query engine requires significant resources just to understand the data structure before we start analyzing. These problems led to the question of whether we could have the best of both worlds. Could we keep the cheap object storage that made data lakes flexible, but add the performance and governance that made warehouses reliable? This was the vision for data lakehouses. Data lakehouses added a metadata layer that acts like a smart catalog on top of object storage. This is implemented through open table formats such as Apache Iceberg and Delta Lake. The metadata contains key information that helps solve the specific problems we've discussed. First, it maintains schemas for data files, giving structure to our unstructured data. It keeps a history of these schemas, which allows them to evolve without breaking queries. Second, it tracks file statistics such as row counts and data filters to optimize queries by skipping files that won't contain the target values. Third, it maintains transaction logs to enable ACID transactions and time travel queries. Finally, it tracks small files and determines which ones can be merged to create larger, more efficient files when compaction is triggered. This transforms the object store into a platform that blends the performance of data warehouses with the flexibility of data lakes. But what about that awkward, unstructured data? This is data that is inconsistent or hard to read, like videos, documents, or variable formats. These files stay in object storage exactly as they are. The lakehouse automatically tracks file-level metadata like size, format, timestamps, and registered schemas. Meanwhile, Custom processing can extract content-specific metadata such as video duration, image resolution, or document properties. This metadata becomes queryable through structured tables, allowing us to preserve the original files while making their properties searchable. Unfortunately, despite progress, there is a gap in the architecture Lakehouses have yet to deal with. Real-time data flowing through platforms like Apache Kafka isn't stored in object storage, so it's not available for analytical queries. This creates friction between streaming data and analytical data in the Lakehouse. Thankfully, Lakehouse architecture provides the building blocks to solve this. Tableflow is a new approach that automatically converts Kafka topics into tables in a Lakehouse. It takes Kafka topics and populates object store files, extracting metadata automatically. This allows business analysts to use familiar query tools on real-time streaming data without building complex data pipelines. It creates a unified platform for querying all data, whether it is from batch or streaming. It makes real-time streaming data accessible as a database table. Historically, each generation attempted to solve some of the weaknesses found in the previous one. Warehouses made analytical queries more accessible. Data lakes added flexibility to handle diverse formats, but at the expense of losing the structure and governance warehouses provided. Lakehouses kept the flexibility of lakes, but restored performance and governance. Tableflow removes the real-time friction. Future technologies may adopt this approach of automatically creating Lakehouse tables for different data types. This will unify these technologies and make data easier to manage and query without complex pipelines. So are data warehouses, lakes, and lakehouses just mumbo-jumbo? Not at all. Each one solved a real problem at the time, and despite how it seems, the names actually reflect the details of the technology. Warehouses store operational data in bulk for analytical queries. Lakes collect data from many sources into one homogenized form, like real lakes gathering water from rivers and streams. And lakehouses combine the flexibility of lakes with the performance of warehouses to give us the best of both worlds. Evolutions like Tableflow will build on these advancements, creating new products along the way. We can still hope for that data duck pond, but now we understand how we got here.